Okay, now another important topic, Riemann sum. So this kind of sums are called Riemann sums. Okay, so we will try to understand this finite sum consisting of n many terms. So this is in fact the sum of the areas of the approximating rectangles. Let me explain how. So this is the area of the kth approximating rectangle. So how? Let me show you through the figures. For example, this is our curve and we want to approximate the area under this curve by using approximating rectangles. Okay, our aim is this one, to estimate the area under the curve by using approximating rectangles. We studied how to do this in the previous section. So you divide the whole interval from A to B into sub-intervals of equal length. And let's say we are dividing now n many sub-intervals. So, okay, so like that. Or like this. Here you have much more rectangles, I guess. And after dividing this interval into sub-intervals like this, for example, we can study on this picture, I guess. This is, let's say, the x0 point, x1, x2, and let's say we are using the midpoints of the rectangles. And let's choose the kth rectangle here. Okay, just let me make it bigger, like, okay, maybe from here I can explain. So let's concentrate on this kth rectangle, which is also over here. And as you can see, they are using the midpoints to create the rectangles. Okay, xk is somewhere here. And let's zoom into this part, make it a bit bigger like this, like that. And the height of this rectangle is coming from the image of this y. Here, it is already here, y equals f of x curve evaluated at this midpoint, right? So the height is given by the image of your curve evaluated at xk point. And the base is, we said that we divide this interval into n many sub-intervals, okay? So here, the last point is, in fact, xn. Starting from x0, x1, and like this, the last midpoint is the xn. So let me say the base, the length of the base of each sub-interval is delta x. So what is delta x? What is the length of each base? It is in fact the total length from A to B, so it is B minus A, divided by the number of rectangles, okay? So we divide into n many sub-intervals. That's why I need to divide by n the total length to obtain the base, okay? Base is given by delta x, which is given by this expression. And then you can easily write a formula for the area of this approximating kth rectangle. So let's denote the area of it by AK, area of the kth rectangle. Kth rectangle is what? Is base times the height. This is base times f of xk, xk being the midpoints times the height. Okay, then since we understand the kth rectangle now, I can try to sum of all the areas of those rectangles from k equals 1 to n, right? Okay. So then I want to write the sum of the areas of all rectangles. Areas of all n many rectangles. Okay, let's say n many rectangles. So I will be summing up these terms. This is the area of the kth rectangle, remember, f of xk, delta x. By the way, let me put the first midpoint as not x0, but x1. So from 1 to n, we have n many rectangles. That's why it will be enough to put the sigma notation here for k runs from 1 to n. So by using the sigma notation like this, I can easily sum all the areas of k n many rectangles like this. Okay, and if I can put the details now, this is the area. This is in fact AK, which we denote by the area of the kth rectangle. And now, okay, this sigma notation, this finite sum will give us the sum of the areas of all such rectangles shown in the figure. We have n many rectangles, that's why the sigma notation starts from k equals 1 to n. And now how to relate this to the exact area? So far, we know that area under the curve, okay, area under the curve y equals f of x is in fact not exactly the same as this. It is approximately the same as this sigma notation. So k is from 1 to n, f of xk. These xk's can be the midpoints, left-hand points, and right-hand points. And in our figure, they are the midpoints, by the way, midpoints of the subintervals. And so this sigma notation gives us the sum of the areas of the approximating rectangles. But as you can see from the figures, this is either lower sum or an upper sum. I mean, this is not the exact area under the curve. But what if I increase the number of rectangles, this number n? What if I send the number of rectangles to infinity? The more rectangles we have, remember what once we said, the more rectangles we have, the less error we obtain. If n, the number of rectangles, goes to infinity, what will happen is that you will get rid of the error terms. And this is the very useful idea how we can express the exact area with a Riemann sum. Okay, so we will be using this idea to express the exact area by using this Riemann sum. By the way, this is called as the Riemann sum, which is already given at the beginning. So Riemann sum is a finite sum like this, which gives us the sum of the areas of the rectangles and many rectangles. Okay, as I said here, if you send n to infinity, this is the only way you can get rid of all the errors, okay? So to be able to write not approximately equal, but exactly equal, what we should add to the right-hand side is this limiting case where n goes to infinity. Okay, let's do that. So if you add here the limit as n goes to infinity, wherein n is the number of rectangles, only then the right-hand side will exactly equal the area under the curve. Under the curve, y equals f of x. And this exact area is denoted by the definite integral notation like this. So exact area under the curve y equals f of x is denoted by this notation. Okay, in the upcoming weeks, we will understand what does this notation mean in more and more details, but for now, it is just a notation for the exact area under the curve for us, and which we call as the definite integral, okay? So definite integral is defined through the Riemann sum with an extra limit notation in front of it. Without the limit, this sum of the areas of rectangles is approximately the same as the area under the curve. You have to use this approximate notation. Only if you send n to infinity, you can get rid of the errors. Only then you can put here the exact equal notation. Okay, so that's all I can tell about the Riemann sum. Let's try to apply all those things to this example. So this is a definite integral. Okay, let me also put the lower bound. This definite integral, it is possible to restate this definite integral in terms of a Riemann sum and find the result. So left-hand side is given, the definite integral part is given. What we want to find is compute the result of this definite integral, which gives us the area under the curve by using the Riemann sum. This is what? This is area under the curve y equals x squared plus 2, and it can be expressed as the limit. As the Riemann sum. What is Riemann sum? Riemann sum is a sum of this form, where f of xk is the height and delta x is the base. So this is in fact the area of kth rectangle, which you can denote by AK, area of the kth rectangle. And if you put an extra limit where the number of rectangles goes to infinity, this definite integral will be the same as the limit of this Riemann sum. Okay, now our aim is to construct this Riemann sum. Let me draw the graph and try to explain you all the heights and bases. So let me create some more space too. Okay, so let me insert and coordinate axis here, like this one, and one more. Like this. Our curve is what? Our curve is this one, x squared plus 1 curve. So let me draw it like this. And I'm interested on this curve over which interval? Over the interval from 1 to 5. Sorry, okay, over the interval from 1 to 5. Like this. Now I will construct my approximating rectangles. So I will divide this interval into n many sub-intervals. Let's say like this. So this will be the 0th point, and I will be using the right endpoint to create my heights. Okay, this is x1, x2, x3, and somewhere here you will have your point xk, like this. And the last right endpoint will be xn. So this way, I divide this interval into n many sub-intervals on which I use the right endpoints to create the heights of my approximating rectangles. Right endpoints. I'm choosing right endpoints. You need to make this choice at some point. Either you choose left endpoints or midpoints or right endpoints. Now let's create a rectangle. So this is the first base. You see, these are the bases of the rectangles. I divided into n many sub-intervals. So, okay, this point is also the right endpoint of the previous sub-interval, like that. So height is here, create your rectangle height. Over the base, create your rectangle height. Over the base, create your rectangle. And the kth rectangle will look like, okay, this is the height now. And over this base, I create my approximating rectangle like this. Okay, I'm always using the heights coming from the right endpoints like this. Okay, for example, this is the height of this kth rectangle, and this height is determined by the function, where the function is x squared plus 1. So f of xk, the image of your function at this point xk, is the height of your rectangle, and so like this. Now I think I am ready to construct the Riemann sum. By the way, let's also put the details like what is delta x here. Delta x is the length of each subinterval here, delta x, delta x. So, and many of them be divided. That's why its length is 5 over 1, 5 minus 1 over n, of course, which is 4 over n. And also, let's try to understand what is this xk point. So, for example, x3 is what? X3 is you start from 1 and you add 3 many delta x's to 1, right? So 3 many means 3 times delta x, and xk in a similar way can be computed by 1 plus, this time you will add k many delta x's to the starting point, which is 1, right? That's why the expression for xk is k times 1 plus k times delta x, so k times 4 over n, like that, where 1 being the starting point. Let me also emphasize it. 1 is the starting point. Okay, then the Riemann sum. Now I'm ready to create my Riemann sum. It is this finite sum where we sum the areas of the n many rectangles, areas of n many rectangles. So this is the area of the kth rectangle. It is delta x, the base, times the height. Okay, this is the base and this is the height of it. So what are they? K is from 1 to n. They are, by the way, this Riemann sum can be denoted as Sn because it will depend on n eventually. So it is k from 1 to n. Delta x is computed here as 4 over n. And this is, in fact, the image of the point xk, where xk is, remember what xk is? We already find this expression for xk. 1 plus 4k over n. So the image of such a point is, in fact, what is the function x squared plus 2? Remember? Okay, let me first write it like so. This is in fact xk squared plus 2, where xk is given like this. So 1 plus 4k over n squared plus 2, I guess. So this is in fact the coming from the height part. This is the base part. So this is f of xk, where xk is given with this expression depending on k and n. This is what xk is. So xk squared plus 2, which is the, plus 2, yes. I wrote it plus 1, but it should be plus 2. Okay, so if we are able to compute this finite sum, which we call as the Riemann sum, then after computing it and then finding the limit of it and as n goes to infinity, we will be done with the result of this definite integral. So what remains is to compute this Sn, and then after finding an expression for this Sn depending on n, we will take the limit as n goes to infinity. So what is Sn? It is k is from 1 to n, 4 over n. So I am directly writing this by computing the square, okay? 1 plus 8k over n plus 16k squared over n plus 2. And then now it is time to distribute all the sigma notation over all the sums. So k is from 1 to n. Just make this multiplication, okay? Compute it. It is 12 over n plus, if you do this computation, you will obtain 32k over n square plus 64k square over n cube, like that. And now distribute the sigma notation over sums to obtain this line. K is from 1 to n, 12 over n, plus k is from 1 to n, 32 n square k, plus k is from 1 to n, 64 n cube k square, like that. And then look at what you have. So this thing, 12 over n, which does not depend on k, right? And similarly, here, this expression does not depend on k. This part does not depend on k. You can just take them out. So this is just a constant, right? That's why you can compute the sum of this sigma notation as that constant times the number of terms. So it will be like 12 over n times the number of terms, which is n. And here what you have, 32 n squared, sum of k from 1 to n k, and take this constant out, n cube sum k from 1 to n k squared. Okay, and now you know the formula for sum of integers, right? So what we have is 12 over n times n plus 32 n squared times, what is the sum of integers formula? It is n times n plus 1 over 2 and 64 n cubed. Sum of the squares formula, it goes like n plus 1 to n plus 1 over 6. Okay, let me also emphasize this part, that we use the sum of integers formula. Okay, now you have lots of simplifications. You see, after doing all those simplifications, you will obtain Sn as this expression depending on n. So Sn is finally, after doing all the simplifications, can be written like this: n plus 1 divided by n, then 32 over 2, and n plus 1 to n plus 1 divided by n cubed. By the way, I think this should be 3, right? Okay, so this is the result of the Riemann sum, in fact. This expression is the result of this Riemann sum. And now we are ready to take the limit of it to find the result of the definite integral. Remember, we were searching for the result of this definite integral, which is given by the limit as n goes to infinity of that Sn thing of the Riemann sum. So x squared plus 2 dx from 1 to 5 is in fact limit as n goes to, normally it is like that, delta x f of xk, k is from 1 to n. This part corresponds to this Riemann sum, but you need to put an extra limit as n goes to infinity, so let's compute it. N goes to infinity of this whole expression. We computed this sigma notation, which gives us the Riemann sum as this expression, remember? So this is the Sn part. Let's just insert it here to compute the limit. Then 32 over 3 and n plus 1 to n plus 1 divided by n cubed. Okay, what is this limit now? So let's try to understand. So this part, obviously, going to, okay, since the degrees are equal, this part, as n goes to infinity, this part goes to 1. And this whole part, okay, again, as the degrees are equal to total degrees are equal, the limit of this part as n goes to infinity will be the ratio of the highest degree terms coefficients. So it will go like 2. That's why the result of this limit is, okay, the result is, I think, 12 plus 16 plus 64 over 3. So this is the result of this definite integral computed by taking the limit of the Riemann sum. I think the hardest or most challenging part is to compute the result of such a Riemann sum. It took for a while for us, and then we just take the limit of that expression. So I stop here. Thank you for your attention.